This lesson is on the first 5 sections in chapter 18. Those are the only sections in this chapter that we're going to cover, and the topic is electric current. But before we talk about electric current, we need to talk about a little bit about electric fields, and I'm going to use a gravity field kind of as an analogy. So if this represents the Earth, if we were to draw lines that represented the direction that a mass would move if it was released near the Earth, no matter where the mass was, it would move towards the center of the Earth. And these lines represent the gravity field lines. And so this is a far away view from the Earth. So if I place a mass anywhere around the Earth, it will move towards the center. But if we look at the surface of the Earth, because this distance, say right here, is about the same as this distance from the center of the Earth, the gravity field is fairly constant near the surface of the Earth. So if I were to place just a little ball, like a baseball or something like that, and I released it, it would move in the direction of the gravity field lines, and it would accelerate. Because it's in a gravity field, it would feel a force, and it would accelerate in the direction of those gravity field lines. So there are some similarities with electric fields and charges that are in electric fields. So if we look at this sphere that has a net positive charge, which means electrons have been removed, and I place a little positive charge near this sphere, because they're both positive, this little charge will be repelled, and if I let it go, it will move away. And so positive charges will move with the direction of the electric field. So I know that it's repelled by this charged sphere, and that is due to Coulomb's law with the electrostatic repulsion. Now, because the electrostatic force depends on how far away we are from the charges, the force acting on this charge is not constant, so we would say that this field is not uniform. One way to create a uniform electric field is to connect a battery to two plates that are parallel to each other. So this line represents one parallel plate, and this line represents another. And because this plate is connected to the positive terminal of our battery, this plate becomes positively charged, which means some of the electrons will move towards the positive terminal, and some electrons, the same amount as a matter of fact, will move towards this plate. So between the plates we create a uniform electric field, and if I place this charge within this field, it will move with the field. So now the force is constant, and it will be in a uniform electric field. So when I connect a battery to these two plates, it creates an electric field between the plates. And the reason I bring this up is that we're going to be using batteries when we look at very simple circuits. And what the battery does is it creates an electric field inside the wires of the circuit. So let's look at what we mean by electric current. First of all, in order to have an electric current, you have to have some source of electric potential energy. And the only source we're going to look at is a battery. Now, you guys know that batteries are rated by voltage. For example, the batteries in your calculator have a voltage of 1.5 volts, and there are 4 of them, and because of the way they're connected to each other, the voltages add, so your calculator actually runs on a 6-volt battery. Now, you're going to hear the words potential difference quite a bit, and potential difference means exactly the same thing as voltage. But what you need to remember about batteries is that they are a source of energy. Now, a volt, in terms of units, because those are the units we use to express voltage or potential difference, is 1 joule per coulomb of charge. So let's look at what batteries do within a circuit. So batteries provide energy to the circuit. They provide the energy to make the electrons move throughout the circuit. Now Now the electrons are already present in the copper wire and the components through which the electrons flow, for example, a resistor or a light bulb, because we're going to primarily concern ourselves with just resistors and light bulbs. So when you connect a battery to a light bulb, the electrons are already there in the wires and in the light bulb filament, and all the battery does is move those charges. It provides the energy for those electrons to move throughout the circuit. And there are some misconceptions about what batteries actually do, so let's look at also what they don't do. So one thing they don't do is supply charge, meaning electrons, to the circuit. And this is a very important concept. The electrons are already there in the circuit, within the wires, within the resistor, within the filament of the light bulb. The batteries just push the electrons. They provide energy to the electrons, which makes them move. And they do not also supply protons to the circuits. Remember, electricity is the flow of charge from one point to another in a circuit, but it's the electrons that actually move, not the protons. So our definition of current, and the symbol we use for current is a capital I, is the rate of charge flow past a point in a circuit. And our units, well, the equation, first of all, capital I is a symbol, is the rate of flow of charge, so delta Q over T. And in terms of units, charge is measured in coulombs, time is measured in seconds, and that combination is what we call an ampere, or an amp for short. And the symbol for an amp is a capital A. So 1 amp of current is a pretty big amount of current, even though it's just 1 amp. So sometimes we talk in terms of milliamps or microamps. And with the metric prefix milli, of course, 10 to the minus 3, and micro is 10 to the minus 6. So don't be surprised if you see these units, and when you have these units and you try and use them in this equation, you need to expand them out. And so, for example, if we have 30 milliamps, you should say 30 times 10 to the minus 3 amps when you're using this equation. So let's look at a picture of a very simple circuit. And again, this is a picture, and we'll change this to a diagram, a circuit diagram with the appropriate symbols in just a minute. So this represents the battery. The end of the battery with the little tip or nub on the end of it, that's always the positive side of the battery, and the other end is the negative side. This is a switch. The lines that connect the switch to the battery are wires, and of course this is a picture of a little light bulb. And so this switch is open, so nothing's going to happen. The light bulb will not light up, because in order for current to flow, there has to be a complete path for the electrons to leave the negative terminal, go through the filament, go through the switch, which is open right now, so this won't work. Has to be closed, so we would move this piece down to here to make that connection, and then back to the battery. But as it is right now, the light bulb will not light up. So again, this is a picture of a simple circuit with a switch, wires, light bulb, and a battery. Now this is the very same picture, but now we call this a circuit diagram because we're using circuit symbols instead of pictures. And this is the diagram you need to be able to draw based on information you're given. So a battery all by itself is just these two parallel lines. One is longer than the other, and the long line represents the positive side of the battery. Our little switch here, these represent the terminals, which are these points right here, and this represents the movable portion of the switch. So once again, this is an open switch. These lines again mean the wire, and this little circle with the little squiggly line in it represents an electrical symbol for a lamp, or what we'll call a light bulb. Now, for most of the time, we will assume our wires are ideal in that they do not offer any resistance to current flow. Now, in fact, that is not quite true, but for our purposes, most of the time we will consider our wires to be ideal. But we do need to talk about the resistance of a wire just for a few minutes, and that's called resistivity. So every wire does actually have resistance in it. Even though we use copper, it's a very good conductor, it does offer some resistance to charge flow. And if you've ever used a power tool like a circular saw for any length of time, after you use it, if you grab the cord, it will feel warm. And that is a byproduct of heat, which is a loss of energy. So here we have a little diagram of a section of wire whose length is L, and the cross-sectional area of the wire is A. And so the resistance of a piece of wire depends on three things. It depends on its length, and it's directly proportional to the length. It also depends on the cross-sectional area, and it's indirectly proportional to the cross-sectional area. And the third thing it depends on is what kind of material the wire is actually made out of. And for example, copper or aluminum or gold or something else. So the equation that relates these three items, the length, the cross-sectional area, and the material, looks like this. So R is our symbol for resistance. This symbol rho is called the resistivity, and this is a constant that is determined by the kind of material the wire is made out of. And there's a table in your book that will list the values for this constant for several given materials like copper or aluminum. As we said, L is the length, A is the area. The unit for resistance is called the ohm, OHM, and the symbol looks like this. It's a capital omega in the Greek alphabet. Now, I doubt that you'll ever have to actually use this equation to calculate anything, but you need to know the relationship between the resistance of a wire and its length and the resistance of a wire and its cross-sectional area. But I haven't seen any problems where you actually have to calculate the resistance given these three variables. But again, most of the time, actually all the time, when we're dealing with circuits like this, we will assume our wires are perfect conductors and they offer no resistance at all. And in reality, copper wires offer very little resistance unless they're really, really long. So it doesn't really come into play that much anyway. But in theory, they do offer some resistance, but we are going to assume that they offer none when we're looking at these circuits. So here we have another circuit diagram. Here's our battery. Now you're going to see this symbol. It's a capital E cursive, and it's short for EMF. And EMF is an old term that scientists first used when they were exploring batteries, and it stands for electromotive force. But it's only used to represent the voltage of the battery. So don't let the E confuse you. It's just telling you that this is the EMF of the circuit, which is a battery. And it does have a voltage, so the EMF might be 3 volts or 6 volts or 12 volts. And here's our switch again. Now the switch is closed, and here's our little lamp. Now, a long time ago, it was not known whether positive charge moved or negative charge moved. So scientists just assumed it was the positive charge. So if it was positive charge moving, it would leave from the positive terminal and make its way through the circuit, through the lamp, and back to the negative side. This direction of current is called conventional current. And even though it is wrong, because now that we know that the electrons are the particles that actually move in a circuit, for whatever reason, and I don't know why, they've decided to stick with the conventional current convention that states that it's the movement of positive charge through a circuit that determines the direction of the current. And I know it's wrong, and you may say, well, that's pretty stupid. Why didn't they change the direction of the current flow? I don't have an answer for that, because I kind of agree it's kind of silly to still use this idea of conventional current. But for our purposes, we will always indicate the direction of positive charge movement as the direction of current. And so whenever you see a battery, just think of positive charge leaving the positive terminal so that it can get to the negative terminal, even though the electron flow is actually in the opposite direction. So conventional current is always positive charge flow. Now, there is a relationship between the voltage applied by the battery, the current through the circuit, and the resistance of